Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with more application of thermodynamics to materials. These are the contents. We'll apply thermodynamics to binary systems. Change in state properties during mixing we will look at. We started about that in the last class. Today we'll continue with the water interaction parameters and enthalpy change and how it affects the phase formation. Then entropy change and how it affects the phase formation. Then the Gibbs energy change. Then we will see what is weighted average of properties, and then partial and integral molar quantities, and finally chemical potential. In the last class we saw this. According to quasi-chemical theory, just the bond energy change is assumed to be equal to delta H, and it can be 0, positive or negative. Based on this we can say if it is negative, it is a non-ideal mixing where interaction occurs, meaning A and B atoms like each other, then we call it negative interaction or attraction. When enthalpy of mixing is positive, we call it again non-ideal mixing where interaction occurs. The interaction here is called positive interaction and atoms A and B repel each other. Whereas this case in the top is called as ideal mixing with no interaction. So this epsilon will consider that as delta H per AB bond, meaning epsilon AB, the final AB bond energy minus average of the initial bond energies of AA and BB, that is going to be epsilon. How to get delta H per mole? Then we have to figure out what are the total number of AB bonds. We can get this delta H per mole. Let's try to do that. In that way, we will find what is an interaction parameter. Consider AB, two element alloy of 1 mole. So Avogadro number of atoms are there. Every atom has 6 neighbors to bond. We call that Z. Imagine something like this where an atom here, it bonds to atom in the top and bottom, to the left and right, and to the one in the front and back. Na multiplied by Z will give us the total number of bonds. Total number of bonds, not just AB bonds. Okay, these are just total number of bonds. In that, how many are AB bonds? Obviously, we need to know what is the composition of the alloy, what is the XA and XB, the mole fractions. So for AB bonds, a site should be A and the neighboring site should be B. Okay, based on XA and XB, we can say XA is probability of finding an A atom in a site is XA and probability of finding a B atom in a site is XB. We have already seen this. Mole fraction is nothing but probability of finding an atom in a site. Therefore, if we multiply XA and XB, we are going to get the probability of finding AB bonds, and that if we multiply with the total number of bonds, we are going to get the actual AB bonds. Therefore, if we take this AB bonds number, multiply that with bond energy of a single bond, single AB bond epsilon, we are going to get enthalpy per mole. In this, if we separate out this part epsilon NaZ, apart from without this mole fraction terms, we are going to get something called omega. This omega is interaction parameter. So you can see that epsilon is captured in this. This is the bond energy of AB. So omega is a measure of that. That is more important. So bond energy is captured in omega. So interaction parameter tells you whether atoms like each other or dislike each other or do not bother about each other. All those stuff are there in omega. Right. So based on this, we can replace this part with omega and write delta H is equal to interaction parameter multiplied by XA and XB. So based on this, whatever we have seen in the previous slide, we are repeating that based on interaction parameter here. So if omega is 0, it means A and B neither like nor dislike each other, meaning they don't bother about who is the neighbor. The bond energy is still same. When omega is less than 0, A and B like each other. If omega is greater than 0, A and B dislike each other. If you see the nature of this XA, XB, you will see one important insight about this. XA, if it increases, let's say from 0.1, 0.3, 0.5, 0.7, 0.9, Accordingly, xb is going to decrease from 0.9 to 1. xa multiplied by xb is going to look like this. You see top value and bottom value 0.09, then 0.21, 0.21. The middle we have 0.25, meaning this is kind of a symmetric distribution. So xa xb is symmetric and maximum is at the middle 0.25. Maximum itself is 0.25. Therefore, multiplying xa xb with any quantity will yield maximum a quarter of the original quantity. We are doing that here. You see, omega we are taking and multiplying that with xa xb. So even if xa xb is maximum 0.25 for this kind of composition, we are going to get omega multiplied by 0.25, meaning delta H will be maximum 1/4 of omega in terms of magnitude. For example, if we take omega as -4 units, if it will be like xb, we are only putting xb here, xa multiplied by xb is going to be here, then omega multiplied by xa xb is here. This is also going to be symmetric. The maximum is going to be this -1 in terms of magnitude. How the actual curve will look, this is an AB system. xb increases like this, meaning this is 100% A, this is 100% B, xb increases like this. And this omega is marked here in y-axis. So that is the interaction parameter. It is constant with respect to composition in this case. Therefore, delta H mix, according to these values here, we can plot delta H mix. It's going to look like this. So this is also symmetric now. Right? If we put the positive omega also, so omega is these dotted lines in the top and bottom. This we have seen this red color stuff in the previous slide. If omega is positive, let's say positive 4, then delta H mix are these solid lines. You can see this is the enthalpy of mixing now, positive enthalpy of mixing. So this kind of solutions where this symmetric delta H mix curve comes is called as a regular solution. Omega is independent of composition here, it's just a flat line, and symmetric delta H mix versus composition curves we see. So delta H mix versus composition is symmetric about the middle. That's what we see. This kind of behavior will be there in many of the solutions, and they are called as regular solutions. The other solutions, omega is dependent on composition. In that case, delta H mix versus composition curves get complex. We will be seeing about that kind of solutions also a lot. Based on this enthalpy of mixing, if we see what kind of phase formations are possible, think about this: 100 atoms, 50A and 50B. In this first case, we see number of AB bonds is 100. In this case, number of AB bonds are 132. In this case, it is 200. All the bonds are AB bonds. Okay. Why these differences come? Based on enthalpy, can we get some insight? The answer is yes. If delta H is 0, we get this. This is a complete random mixing. We call this ideal solution. If delta H is less than 0, then we get this. We call this short range order, meaning the number of AB bonds are more. There is some kind of a preference between A and B. Delta H being negative means A, B atoms like each other. Then this is a non-ideal solid solution. We still call it solid solution, and it is non-ideal where A and B atoms tend to bond together more compared to this ideal case. This one is when delta H mix is highly negative. Okay, in that case, long range order happens. This is not called a solid solution. This is an intermetallic compound. Only A and B atoms form bonds, not AA or BB. Here you see at least some orange and blue bonds. Here nothing like that. All the bonds are between orange and blue. This is the other side of the spectrum where delta H mix is 0. We call this random mixing. Where if delta H mix is higher than 0, then here number of AB bonds are coming down, meaning this is a clustering. Clustering happens again in non-ideal solid solution, and AA and BB atoms tend to cluster together. You can see orange atoms going together and blue atoms going together, meaning AB bond is not preferred. A and B do not want to bond. AA bonds and BB bonds are preferred. In this case, delta H mix is extremely high, highly positive. In that case, you hardly see any AB bonds happening. and this can be called as unmixing or no mixing. This can be imagined as if the initial two metal pieces that we take, A and B, did not even diffuse into each other and formed anything, right? This can happen when delta H mix is highly positive. So here it's no more single phase, it's two solid solutions. AA and BB atoms tend to go as separate phases, and there is even grain boundary formation because it is between two different phases. That grain boundary is called as interface that forms. Right. Now comes one question of curiosity. Now when we said delta H is less than 0, we said A and B attract each other, right? If A and B attract each other, then why do AA and BB bonds exist here? Why not have only AB bonds completely? Okay. What allows some AA and BB bonds to exist in this case? Okay. This is one question of curiosity. Here delta H, when it is 0, random solution, the ideal solution, in that case A and B neither attract nor repel each other, right? In that case, why do AB bonds exist? Why not stay as AA and BB bonds itself? We start with anyway something like this, right? Only AA bonds and BB bonds are there. Then why should they not stay like that? A atom anyway do not bother about the neighbor, whether it is A or B, the bond energy is same, right? Then why AB bond should form here? There are orange and blue bonds, right? Why do they form? 100 bonds we are saying for AB. Why do they form? They can be separately staying like this, right? So this is another question of curiosity. Okay. For this kind of effects, the reason is actually entropy of mixing. To understand entropy of mixing, let's consider mixing of ideal gases. Let's say two different ideal gases are there, separated by a wall now, and they are now moving within their chambers. Once the partition is removed, they are going to intermix. Right? Now it went from this state of separated state to this kind of mixed state. The natural process happens in this direction. What drives this change? The question is asked here because the gases here have no enthalpy of mixing, no attraction or no repulsion. In that case, can they be expected to stay separate when the partition is removed because there is no attraction between two different types of gases? Or once they mixed, can they separate to initial state spontaneously? Intuitively, you know that this is not going to happen. The reason is there are simply immense number of ways to be mixed than to be unmixed. We are talking about the W now. If you recall, the system goes from low W state, meaning when the two gases are in their separate chambers, that's the low W state, to a high W state, that is the mixed state. Right. Entropy of mixing is positive, and that's the one which drives the mixing. So when enthalpy of mixing is 0, entropy of mixing makes the entropy change makes the mixing possible. Right. So this is what happens in this case. In solids, we call it chemical configurational entropy. Let's understand what is that. We have already introduced this term. Here if you see in this solid solution, PAB equals 100, that is the kind of macro state we have. If the atoms shuffle, exchange their positions, now the number of bonds, if you think, are changing, it is not so. That kind of shuffling is possible, but still the total number of bonds can remain the same, PAB equals 100. So a large W arises, number of ways of arrangement arises of chemical species for the same macro state, that is the same number of bonds. PAB equals 100 can be maintained, but atoms can shuffle each other and get themselves arranged in multiple number of ways. Okay. So this can be used, this W can be used and an entropy can be calculated. This is called as configurational entropy widely, but strictly speaking, a better name would be chemical configurational entropy due to different ways of arrangement of chemical species. This chemical configurational entropy change favors this PAB equals 100 bonds of AB, that is the random mixing. This is the most random mixing possible, meaning maximum number of W corresponds to this. So that's what is driven by the chemical configurational entropy. The macro state with the maximum number of W. So this is why AB bonds form even when delta H is 0. Okay? They could have stayed all blue atoms on one side, all orange atoms on one side, but they don't do so. They get mixed like this and form some number of AB bonds because it is driven by maximizing W. This chemical configurational entropy thus favors PAB equals to 100 in ideal case where delta H is 0. What happens when delta H is negative? Okay, PAB equals to 132. We saw this kind of case. We said it is short range ordering. Some number of AB bonds is definitely more here compared to the ideal mixing. But if delta H is less than 0, meaning A and B attract each other, right? So why not all the bonds become AB bonds? Why should there be some AA and BB bonds still left? Okay. Enthalpy of mixing favors all bonds to be AB, that is PAB equal to 100. But enthalpy competes with the entropy. Okay, enthalpy of mixing and entropy of mixing compete. So only short range order occurs depending on the actual magnitude of these competing effects. See, PAB is now in this case 132, definitely not 100. More number of AB bonds are there, but definitely not 200 also, somewhere in between. This is what happens when delta H is negative. When delta H is positive, number of AB bonds go down from 100. AA bonds are more, BB bonds are more, and AB bonds are less. Okay, we called it clustering. Enthalpy of mixing favors AA and BB bonds. That is, it does not favor AB bonds. PAB equals to 0. Okay, enthalpy and entropy of mixing compete, and only clustering occurs depending on the actual magnitude of these competing effects. In this case, the enthalpy is only positive enough to make PAB 62, not 0. But the entropy of mixing also cannot bring it up to 100, it can only bring it up to 62. Right, extreme non-ideal cases we will see now, where it is mostly driven by enthalpy change and possibly by other entropy changes, but the chemical configurational entropy clearly fails to dominate in these cases, where when delta H is highly positive, PAB is only 8 here, is as good as 0. This we call it unmixing or no mixing. Enthalpy of mixing favors no AB bonds, that is PAB equals to 0, and it dominates. This enthalpy of mixing dominates, therefore no randomness in chemical species in lattice sites occur. Okay, there is no possibility of A and B mixing and forming some kind of a random PAB number of AB bonds randomly arranged. So that is not possible here. So no chemical configurational entropy change occurs here. When delta H is highly negative, then enthalpy of mixing favors all bonds to be AB, that is PAB equals to 200, and this dominates. The magnitude is so high, so it dominates, and no randomness in chemical species in lattice occurs. Why we say this is no randomness? Because all orange is surrounded by blue. There is nothing called AA bond and AB bonds and BB bonds, all are there together, nothing like that. All bonds are AB bonds. This is a perfect chemical order. Okay, so no chemical configurational entropy change can occur. These cases are more like in the coin example, the 1000 coins we took, initially everything was heads and then we started shaking, so they got randomized, right? These two states are almost like the 1000 head cases. Okay, the W is only one. There is only one way to get all this AB arranged in this perfect crystalline order that we are seeing here. Okay, so this is like W is equal to 1 kind of states. This is what happens when delta H is too high in its magnitude, so that the entropy which tries to randomize the structure cannot dominate at all. So that's about the chemical configurational entropy change. What about thermal entropy change? Okay, if we take this delta H being highly negative, non-ideal mixing, bond length and stiffness values change, vibrational energy levels change, therefore change in vibrational entropy occurs. Okay, similarly, electronic and magnetic entropies may also change. Okay, in general, we can say, putting together all these things, thermal entropy changes. Right, only about ideal cases, if we summarize what we have understood in ideal mixing, thermal entropy doesn't change, enthalpy doesn't change, only chemical configurational entropy changes. Mathematically, what is this chemical configurational entropy? If we take Na number of A atoms and Nb number of B atoms, 1 mole in total, and this initial state gets converted to this kind of mixed state when delta H mix is 0. Chemical configurational entropy we can calculate now by taking this initial state. The W in this initial state is 1, number of ways in which the chemical species can arrange, all A on one side, all B on one side, only one way to do this, so W initial state is 1. Final state is, for the final state we can calculate WF like this. Then if we calculate the configurational entropy of mixing, delta SC, K natural log of WF minus K natural log of WI. In ideal mixing, this delta S mix ideal, total entropy of mixing itself is equal to configurational entropy of mixing, chemical configurational entropy of mixing, nothing else. And this value minus this value Wi, if you substitute, this value is going to be 0. So we can write delta SC ideal is equal to K natural log of WF. How do we get this? From this, if you see, there is something called a Stirling's approximation. If you apply this formula and take this Na number of A atoms here in terms of mole fraction, if we want to write it, XaNa, the Avogadro number of atoms here, that if it is multiplied with mole fraction of A, we will get the number of A atoms, right? So if we do this, substitute these things here, then simplify, we will get this. I'm not going through the entire steps here. This is quite an elegant formula to understand. Delta SC ideal is equal to R multiplied by XA ln XA plus XB ln XB. So just mole fractions are there, nothing else. Okay. So if this is done for binary alloy, AB alloy, we can calculate the configurational entropy of mixing. In the ideal case, that is nothing but the total entropy of mixing. There is no thermal entropy change. For multi-component systems, we can write like this. Instead of just A and B, we'll write Xi ln Xi and summing over all the i's. So Xi is mole fraction of ith element in a multi-component system. The expression is true in ideal mixing when the mixing is fully random. This expression is true only for the random mixing, fully random mixing cases. In non-ideal mixing, where mixing is not fully random, a deviation from this formula may occur. But in regular solution model, we introduced regular solution few slides back, where the enthalpy of mixing is symmetric. So that the regular solution model, this deviation from this formula, whatever we are talking about here in non-ideal mixing, is ignored. Of course, when we say regular mixing, regular solution, we are talking about delta H mix. We say that is symmetric, but there is a delta H mix. It is not 0. But although delta H mix is not 0, we don't treat this mixing as not random mixing. Okay, we still treat it as a random mixing and use this formula. Okay, that is regular solution model. This can be used for some cases, but not in all cases. Delta SC regular, for regular solution, the configurational entropy of mixing is equal to configurational entropy of mixing for ideal cases. In fact, in regular solution, it is assumed that delta S mix regular is equal to delta S configurational ideal, meaning delta S mix regular. When we put delta S mix, we are also bringing thermal entropy and all into picture, but those things are ignored and only delta SC ideal, meaning configurational entropy alone, is considered as the total entropy of mixing in regular cases. Okay, so entropy of mixing has only chemical configurational entropy contributions, but this is not a good approximation in many cases, since the deviation from this formula can be significant, especially when the enthalpy of mixing is high. Enthalpy of mixing, when it goes high, you know what will happen to these bonds and all, right? So if that happens, the total random mixing is broken. If that happens, then this formula cannot be used. Okay, so when enthalpy of mixing is high, we have to be careful. And other entropy contributions may also be present. So one has to be careful about all that. Meaning, if you want to calculate entropy of mixing, you can't only say entropy of mixing is equal to this formula. How it looks graphically, delta SC ideal versus composition, if we draw, this is going to look like this. When XA and XB is 0.5, delta SC ideal reaches 0.69 R. This value becomes 0.69. So 0.69 R is the maximum value of delta S that we can get, this configurational entropy of mixing. That's the maximum we can get, and it is symmetric with respect to composition. We can see that. What is important about this configurational entropy based on this formula is this entropy depends on only the number and content of elements. Here two elements are there, A and B, and their content is XA mole fraction and XB mole fraction. Only those things matter in this formula, nothing else. It does not depend on what actually are the components. Whether the A is copper and B is nickel, or A is chromium, B is iron, doesn't matter. What matters is how many number of elements are there and what is their content, what is their composition. That's the only thing matters here. And temperature also. Also it does not depend on temperature. You see in this equation there is no T. Okay. So this formula doesn't have any T, so temperature dependency is also not there for this calculation, right? That's about the entropy of mixing. What about the Gibbs energy of mixing in ideal cases? Delta G mix ideal is delta H mix ideal minus T delta S mix ideal. And we know if it is ideal, delta H mix ideal is going to be 0, and delta G mix ideal is nothing but minus T into this whatever we saw delta S mix ideal. So T delta S minus T delta S is the delta G in the case of ideal mixing. Graphically, if we put this delta G minus T delta S mix ideal, we have seen the delta S mix case, the curve was looking like this in the previous slide. If we multiply that with minus T, how is it going to look? It is going to look like this, right? So this is the Gibbs energy of mixing for ideal case. If we move on to non-ideal cases where delta H mix will have a value, consider delta H mix as negative for the first consideration, and delta S mix is approximately equal to delta S mix ideal. Okay, what we assume in the regular solutions, that kind of thing. Let us say delta S mix is not very different from delta S mix ideal. So if we plot it now, this is the minus T delta S mix. Then this is the delta H mix. We said delta H mix is negative. This is going to look like this. And delta G is delta H minus T delta S. Now delta H is negative, we said. So there is going to be a negative entity minus T delta S mix. So what we are essentially going to do is these two things we are going to add up, and we are going to get a highly negative value delta G mix. This is what happens when delta H mix is negative. When delta H mix is positive, what will happen? This term will be positive, this will be negative. So if those two compete with each other, this is the delta H mix and this is the minus T delta S mix. Ultimately delta G mix is going to be like this. Now what is important here is delta H mix is positive, meaning A and B do not like each other. But delta G mix is negative. Ultimately what is important is delta G. Delta G tells you whether mixing is feasible or not, because here delta G mix is negative. We are putting it below this line, right? So this is the 0. Below that we are putting this delta G mix, so that is negative. Why it has become negative? It is because of minus T delta S. This is the one which pulled it to the negative side. Okay. So this is why we said although delta H mix is positive, there is a possibility of mixing because of delta S mix. That's the one which drives it. So that makes the total delta G mix negative. Okay, if delta H mix is highly positive, okay, then what happens? Then entropy of mixing cannot dominate and bring the entire delta G mix as a negative value. Delta G itself goes up. When this goes up, then interesting phenomena like phase separation and all come into picture. We call this immiscibility. When they nicely mix, we call it miscible. When they go away from AB, go away from each other, we call it immiscible. That immiscibility will happen when delta H mix dominates the T delta S mix. Now let's see one more interesting idea, weighted average of state properties. We will see about enthalpy as the weighted average. To do that, let's consider this pure A and pure B. The mole fraction of A and B are XA and XB. And if we put it graphically, we are going to put the enthalpy now. Enthalpy of pure A and pure B are HA and HB with respect to some reference state. Let's put them here, HA and HB. Then before mixing, it's called as mechanical mixture. Consider an overall composition of XB 0.5, XA 0.5, right? So we are going to put it here. This is the overall composition now. At this composition, where these two things are there before mixing, what is the total average enthalpy? We are going to put it here, right? This is the average enthalpy between this and this. Nothing but enthalpy of mechanical mixture. What is this? Mole fraction of A multiplied by HA plus mole fraction of B multiplied by HB. That is the mechanical mixture's enthalpy. It is weighted average of unary enthalpies. Each element's enthalpy is weighted with its mole fraction and summed. What we are doing is, if we take this value, HA value, multiply that with mole fraction of A, this is going to become like this, multiplied by a fraction, so it is going to become like this. Similarly, this side, this is the enthalpy of 1 mole of B. If we multiply that with the mole fraction of B, we are going to get a smaller value. Adding these two things, we will get the enthalpy of the average enthalpy here, which is called as weighted average. It is for this point, this overall composition. Instead, if we go all the way from here, then we'll have all these compositions, right? For all those compositions, this line traces the mechanical mixture Gibbs energy. So the equation for this line is HI equals XA HA plus XB HB. Very straightforward idea, but quite useful. This thing HI is called as mechanical mixture enthalpy or a reference enthalpy value. Since mixing enthalpy is found with reference to this value, that is the important point. Therefore, if we talk about state properties of binary phase, in the mechanical mixture stage, this is just the weighted average, and after mixing, after the solution formation, to this weighted average, we are adding delta H mix. If we do that, we get the enthalpy of the final state. Weighted average of unary state properties, which is this part, plus changes on mixing reaction or formation. In this case, A and B are nicely mixed. Similarly, this is for the Gibbs energy. This is weighted average of Gibbs energy before mixing. This is after mixing, where delta G mix is added to the weighted average. This weighted average idea is going to help us understand what are partial and integral state properties. What are we talking about? Partial and integral state properties. This thing is what we have seen. GA is Gibbs energy of the mechanical mixture. GA and GB are the Gibbs energies of pure A and B respectively. And GA is the weighted average of GA and GB. What we are talking about is this side. Now what about this side here? We can write this equation also like this, which looks similar to this equation. So instead of just GA, we are putting GA bar. Okay, so GA bar and GB bar, what are these things? G phi, this one, Gibbs energy of the solution, or integral molar Gibbs energy of the solution if we express it by if we express it per mole. Okay, integral molar Gibbs energy or integral Gibbs energy per mole, right? And GA bar and GB bar are Gibbs energies of dissolved A and B in the solution respectively. Or in other words, partial molar Gibbs energies of A and B in the solution. Because this is just part of the total is integral. These are partial molar Gibbs energies of A and B in the solution. Okay. G phi is the weighted average of GA bar and GB bar. So what are we talking about here is pure A and pure B Gibbs energies. If we take and average it, we get the mechanical mixture Gibbs energy, and dissolved A and dissolved B's Gibbs energies if we take and weigh it, then we get G phi. Meaning the A when it is in pure form and compared to the A which is in the dissolved form. In these two cases, the element A is going to have a Gibbs energy difference. Initially it was having only AA bonds. Now it is having AA bond, AB bond, everything, right? So definitely there is a change in Gibbs energy of A. So if Gibbs energy of A changes, similarly Gibbs energy of B changes from its pure state to the dissolved state. So in the dissolved state, the Gibbs energy of A alone and Gibbs energy of B alone is nothing but the partial molar Gibbs energies. Okay, in the dissolved state. In the pure state, they have a different Gibbs energy. Right? Now we look at the idea of chemical potential. Let's bring what we saw in the previous slide. This GA bar and GB bar are also expressed as mu A and mu B, the chemical potential of A and B in the solution respectively. Okay, so chemical potential and partial molar Gibbs energy are same. So based on this, we can write G phi equals XA GA bar plus XB GB bar, or XA mu A plus XB mu B. This idea of chemical potential is quite important in open systems. Open system is where mass exchange happens. Consider A or B is added to an existing AB system. Okay, there is an AB solution and 1 mole of A is added now. What will happen to this A? When it dissolves, obviously its Gibbs energy is going to change compared to its original state, right? So how much of that Gibbs energy change will happen? That's what we are calling it as chemical potential. You see this. Chemical potential of A is the change in Gibbs energy per mole of A, at constant pressure, temperature and number of moles of B. Meaning mu A phi is equal to dG phi by dNA, where NB, P and temperature are constant. Meaning everything else, the pressure, temperature is constant, number of moles of B is constant. Then if A is added, the Gibbs energy of only A is going to change, right? So how much ever the change in Gibbs energy of A happens is the change in Gibbs energy of the system, right? Because everything else is now constant. So this is what we define formally as chemical potential. So this is equal to Ga bar phi, okay, dG phi by dNA, exactly same. These two are same. Chemical potential is partial molar Gibbs energy. So partial molar enthalpy also we can write similar to that, and partial molar entropy also we can write similar to that. Partial molar enthalpy of A is the change in H of A per mole of A at constant pressure, temperature and number of moles of B. Similarly, partial molar entropy of A is the change in S of A per mole of A at constant pressure, temperature and number of moles of B. And this chemical potential we are going to use quite frequently. So just treat it as Gibbs energy of elements in the phase, in the solution or in the compound. That's what chemical potential is. Okay, we are going to express it per mole of that element, like how it is done here. Thank you. I hope the lecture is useful. See you in the next class.